Welcome everyone in the third talk of Sukanta Das, and today we will be talking about some properties of the Julia set and the structure of the Fatou components. Sukanta, over to you.
Okay, thank you. Okay, so maybe I'll recall some definitions from the last talk, and then I'll proceed. So, unless otherwise stated, we'll talk about rational maps of degree at least 2. So, say R is a map from C hat to C hat. We'll always consider the map of degree at least 2 because the case of degree 1, it has already been discussed in the first lecture. So, yeah, so now, and as we talked about the points, say Z0 is a point on C hat, the grand orbit of Z0 is denoted by this box Z dot. It is the collection of those C in C hat such that R n Z equals to R m Z0 for some m n in n union 0. So, and as I told earlier, that this set is not exactly equal to the forward orbit of Z0 union backward orbit of Z0. Further, there are more points. Yeah. So now, and we talked about an exceptional point that exceptional points are basically those for which the grand orbit is finite. Basically, the set of those points in C hat such that grand orbit of that point is finite. And we said that this is equivalent to say that the backward orbit of this point is finite for rational. But for the transcendental setup, the definition of exceptional points for transcendental entire case, the set of exceptional points is defined by those points Z in C, or you can take even C hat, such that the backward orbit of Z is finite. So what is the difference between the rational and transcendental case is that, so if I give you an example, you can understand that, say, if you take fz equals to ez, then C z equals to 0 is an exceptional point of this function because 0 has no pre-image. That means the backward orbit of 0 is empty. So this is an exceptional point. But if you take the forward image of 0 of Ez, then it is an infinite set. So yeah, so this equivalence does not hold for transcendental setup. Okay, now just these are the simple things which I talked earlier. Now and the earlier day I showed that this I proved this that for a rational map of degree at least 2, the set of all exceptional points, which was denoted by say E, the set of all exceptional points, the cardinality of E is at most 2. And this holds true for transcendental case also. Now, just some quick notes. Okay, so for okay, so these exceptional points for rational map are periodic. Indeed, these points, if say xi be an exceptional point, then xi is either a fixed point or xi is a two periodic point, nothing else. Okay, and for this is for rational, and for transcendental, for transcendental case, all Picard's omitted value omitted value omitted values are exceptional points. But there can be some points which is not an exceptional value, which is not an omitted value, but still it is an exceptional value. So for example, to simply consider fz equals to say z ez, then you can see that z equals to 0 is not an omitted value, but still it is an exceptional value. Maybe sometimes I'm writing exceptional point and sometimes I'm writing exceptional value. Maybe these are confusing, but yeah, these are same. Exceptional point, and here I have written exceptional value. So basically, I mean to say these are looking. So I look at these points like these are like points, nothing else. Okay. Okay. Now, yeah. Okay. Now maybe I'll talk about one more thing. That one more note is that for rational maps, these exceptional points lie in the Fatou set always. But this doesn't hold for this is not true for transcendental, because I'm saying, because as you can simply take the counter example, like just say fz equals to ez. So for this function fz equals to ez, or the Julia set of this function is basically c hat. So but the point z equal to 0, this point is an exceptional point. Also, this point lies in the Julia set, since the Julia set is exactly C hat. So yeah, so these are little differences between transcendental setup and rational setup. Okay. Apart from these, okay, so I'll move on to some properties of Julia set. So this is my result. One, the first one is that Julia set of a rational map of degree at least 2 is infinite. And further, the Julia set of R is either C hat or it has empty interior. So by this statement, you can just visualize what kind of like what are the possible Julia sets of a rational map. See, it has this statement is a big statement. Like either the Julia set is C hat or it has empty interior. Okay. So yeah, now yeah, the proofs are not difficult. Maybe I'll just give some hints and proceed. So yeah. So suppose for the first one, if you assume that the Julia set of R is empty, just empty set, then that means what? The Fatou set is exactly C hat. That means the map, the sequence of function, this is normal in C hat. Yeah, because if the Julia set is empty, that means the Fatou set is exactly C hat. So the sequence of functions forms a normal family in C hat. So in this regard, yeah, like one can show that if this happens, that then there exists a subsequence, say R nk of Rn such that each of the maps in this subsequence has each of the maps, yeah, has the same degree. So yeah, this needs to be proved, but yes, I have just written it here because yeah, because if time permits, then I'll come back to the proof. Then this means that like in this case, what can be the possibility of the degree of the map? Since we know that degree of Rn can be written as the degree of R to the power n. So this fact says that this fact say this is 2 and say this fact say this is 1. So these two facts imply that the degree of the map cannot be anything rather than 1. So if the map is bigger than 1, then this becomes false. So that means our degree of the rational map becomes 1, and which is not the case because we have earlier assumed that map has degree at least 2. So that means we know at this stage that the Julia set of R is at least non-empty. So now the question is how so how is it an infinite set? So it can be assumed that like it can be uh, thought of like this, that if the Julia set of F is empty, sorry, not empty, finite. It's finite. Say something Julia set of, say something, some elements are there. Say B, C, D, I don't know which are there. Yeah, some elements are there. Then see that as I earlier talked, talked that uh, Julia set is a completely invariant set. So all the elements of this set becomes exceptional point. It's, yeah, exceptional points of F, which is not the case because I have said here that Fatou, have I said it here or not? So, yes, this one. For the case of rational maps, all the exceptional points lie in Fatou set. So I can give you the idea why it is so. So that is why if I take my Julia set to be finite, in that case all the elements becomes exceptional. So in that case we have contradiction. So that means the Julia set must be an infinite set. So maybe I can say something here that why is it so? Because if you take a rational map, as I have seen that at most 2 points can be exceptional. So if a rational map say R has one exceptional point, say alpha, then the rational map is conjugate to some polynomial, say P, for which this alpha corresponds to infinity. And I have already said that for a polynomial, infinity is always in the Fatou set. That means your alpha will be always in the Fatou set by conjugacy. Similarly, if your rational map has say two exceptional points, say alpha and beta, then you can find a conformal map for which that R can be conformally conjugated to a polynomial of the form Pz equals to z to the power d. And in this case, your alpha and beta will correspond to 0 and infinity. Now see that for this map, 0 and infinity lie in the Fatou set. Because why? Because 0 is in the attracting domain, because 0 is a fixed attracting fixed point of this function, and 0 and infinity is in the basin of infinity is always in the Fatou set, as I have told. So that means 0 and infinity are in the Fatou set of Pz. That means alpha and beta will always be in the Fatou set of Rz. So that means in this way, all the exceptional points for a rational map lie in the Fatou set. Yeah. So now, so that means we have got that the Julia set is infinite. Now we want to show that it is either C hat or it has empty interior. Second part. So suppose let Julia set of, say, I'm writing sometimes R and sometimes F. I think it is confusing. Okay, so yeah, so you can stick to R. Let this Julia set is a proper subset of C hat. Then I will show that the Julia set has empty interior. So now, so far we have seen that Julia set is the smallest closed, completely invariant set. So now, if you maybe I can give this an exercise. One can try that if you just take the derived set of the Julia set, say J dash, this is the derived set. Then it is an important it will be a good exercise to check whether this J dash is completely invariant or not. It will be completely invariant. And since my J is closed, I can write J dash is subset of JR. And then what I am getting is that if we consider the Fatou set of R and I take the union with this J dash, I will get that this becomes a completely invariant set. Because my Fatou set is completely invariant and J dash is also completely invariant, so their union will be completely invariant. So, and obviously this is closed. So that means I am having by the minimality of J that J is the smallest closed completely invariant set, and I have also got here one completely invariant closed set. I can say that the Julia set of this will be subset of the Fatou set of R union J dash. So that means yeah, the Julia set cannot lie inside the Fatou set. That means Julia set will be subset of J dash, and that means interior of Julia set is 5. Okay. So that means, yeah. So here is a note that, moreover, one can say this: Julia set of a rational map of degree at least 2 is a perfect set, perfect and uncountable set. Yeah. Okay. So now, and maybe for transcendental case, I shall say something for transcendental case. Julia set of a transcendental interfunction is always unbounded. So this is a big difference from rational case, because for rational maps I have seen that there are many polynomials which has a bounded Julia set. Yeah, but for the transcendental setup it has unbounded Julia set. Okay, so this I think, yeah, after this I will come to these are the properties. Okay, maybe I will give some example and then move on. Some examples. So if you take a rational map of this form, say this is translation, or if you take to be a z where modulus of a is strictly greater than 1, then you can find that the Julia set of R is empty in this case. And these things have already been discussed in the first lecture. Now, one can ask, okay, so we have rational maps for which the Julia set is empty. So is there any rational map for which the Julia set is exactly C hat? So this will be a good question to ask. So yes, it is indeed possible. So the example is that if you take a rational map of this form, so z square plus 1 whole square upon 4z 1 minus, okay, not 1, okay, write it like this, yeah. So this rational map has Julia set, which is exactly equal to C hat, and it was proved in 1918. So yeah, one can look the proof in Bearden's book. Yeah, so there are many maps for which the Julia set can be exactly C hat. Okay, now it is an important result. I'll call this as like
Sukant,
X. Yes, yes,
I have a quick doubt.
yes, yes,
So, in the second case of rational map, where you have said like Julia set of R is phi, so in this case,
yes.
zero is a repelling fixed point, na?
0 is a refilling fixed point. Correct. Yes,
So
correct.
is it have to be in a Julia set?
Yes. No, you are saying for the
So you
second
are
case
saying
like this.
yes, second no first case,
Okay, first
second
one.
part.
Okay. Ah, yes, yes. This function.
So Julia set of R is phi.
Yes.
Is it?
Yeah. 0 is a fixed
Ha-
point, and if you take the multiplier, it will be modulus of just a. And if you take the modulus, it is greater than one.
So
So
it
that
have to
means
be in a Julia. So
okay. Maybe
that
yes.
point
You are
have
right.
to be repelling.
Yes.
I think first case is correct
Okay.
that I
Yes. Yes.
understand, but second
Okay.
case.
Yes. Correct. You are correct. It is yeah. This is not the case. Yeah. For the yes. Thank you. For
Yeah.
if you take thank you rz equals to az, then yes, yes, geo is a repelling fixed point, so it goes to the Julia set. Yes, correct. Yeah. So yeah, you just remove this example.
Yeah, first is fine. Yeah, translation is
Yes.
fine.
Correct. Yeah, correct. Thank you. Okay, now yes, so I'll talk. Yes, I'll call this as expansion property. So it says that if you take any open set, let W be an open set which intersects a Julia set, then C hat minus E means the set of all exceptional points. This will be inside this union. Moreover, you can show the same thing for the Julia set, but in this case, the Julia set will be a subset of Rn W for sufficiently large n. So maybe I'll give some quick proofs that, okay. So first of all, assume, or you can just take a set, say it is set W naught, which is the union of n equals to 0 to infinity Rn W, and you take a set K, which is C hat minus W naught. Now, I want to know what is the cardinality of the set K. So if the cardinality of the set is greater or equal to 3 by fundamental normality test, I have mentioned this thing in the first talk. Um, some call, yeah. Yeah. So now, yeah, by fundamental normality test, yeah, I can say that my sequence of this family of functions is normal in W. That means my W is in the Fatou set of R. But this is not the case because my W intersects the Julia set. And I am saying here that my W lies in the Fatou set. This is not the case. So that means the cardinality will be at most 2. Therefore, my W naught is either C hat or C hat minus some point A or C hat minus some point A comma B. So these are the 3 possibilities. Now you take any point Z from C hat minus exceptional terms. Because ultimately I want to show that C hat minus E is a subset of this. That is why I have taken a point Z from C hat minus E, and I want to show that Z belongs to that union. So that means if this Z lies in this shape, then I can say that W naught will always intersect the backward orbit of this, because my Z is not an exceptional point. Because that is why it has infinitely many points in its backward orbit. So that means you can find or you can choose a sufficiently as according to your choice. There will be some natural number, say in naught, such that the backward orbit of these intersects are in naught of W. That means what? There exists a point W in say capital W such that R in naught plus K W equals to Z for some K in say N union 0. That means your Z belongs to the union of N equals to 0 to infinity Rn W. So that means we have proved that my C hat minus E is a subset of union N equals to 0 to infinity Rn W. As I have already told earlier that the exceptional points always lie in the Fatou set for rational maps. So that means the Julia set is a subset of this map. So I can say that my Julia set is always subset of this, correct? So now it remains to prove that my Julia set will be like for some sufficiently large. So yeah, so maybe I can also give this an exercise. So yeah, so this proof also is not difficult. Now I will talk about the relationship of periodic points and Julia set. So this, yeah. So here I'll write a couple of results related to this periodic points and Julia set. And yes, obviously this is not that much trivial. So one always needs a proof. So we can always refer to that Bearden proof. So let me write one by one. These are very, very important. The first one I'll start with is that you can say Julia set as well as Fatou set. Because if you study the periodic points, you can talk about its Fatou set and Julia set. So the first one is that if suppose so everywhere R is a rational map of degree at least 2. So if alpha is an attracting fixed point of R, then we know that for attracting case R dash alpha, this modulus is less than 1, and indeed this alpha belongs to the Fatou set of R. So attracting fixed points are always in the Fatou set of R of that map. So generally, you can say that if your alpha, suppose, is a p periodic point it is a p-periodic point. Suppose you have alpha, then alpha 1, then alpha 2, dot, 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 say this is alpha p minus 1. And in the next stage, to map it, it comes back to itself. So it is p-periodic. And if R p derivative alpha is strictly less than 1, then the cycle, that is alpha 1, alpha 2, dot, dot, alpha p minus 1, this cycle this cycle lies in the Fatou set of R. Also, point each point lies in some Fatou component of R. So yeah, this is quite nice, but for the for the repelling and indifferent fixed points, the this has a connection with Julia set. So that is now I'm going to talk about. The second one is that if this Rp derivative alpha is strictly greater than 1, then, so I'm talking about this generalized case, not always for fixed points. If this is greater than 1, then similarly these points alpha 1, all these points alpha p minus 1, this cycle lies in the Julia set. So in particular, one can say that repelling fixed points are in the Julia set. The complexity comes when we talk about indifferent fixed points. So in this case, Rp derivative at alpha is 1. So there, we know that there are two possible cases, when it is rationally indifferent, when it is irrationally indifferent. So for rationally indifferent fixed, for rationally indifferent points, okay, so if alpha is rationally indifferent fixed point of Rp, then alpha lies in the Julia set of R. But we don't have any definite answer for the irrationally indifferent case. So it sometimes lies in the Fatou set and sometimes it lies in the Julia set. Okay, so the fourth one is that the Julia set of the rational map is the derived set of all periodic points. So if you just collect those periodic points and take the take the set and take the derivative, take the derived set of the set, then the Julia set is same as this derived set. Further, this is more important that the Julia set of R, this is the closure of all repelling periodic point of R. So that means if you can just study what are the repelling periodic points, then if you just take the closure, then you can see that the Julia set is the closure of that set. So yeah, these are not trivial statements. These need a proof. Yeah, so one can always refer to that proof. So I'm just keeping this because if I go with the proof, then I cannot cover the rest of the things. So I'm just giving the idea about the connection of these periodic points with Fatou and Julia set. So that is why I talked in the last lecture that periodic points sometimes, not sometimes, I'll say, like most of the times, it controls the dynamics of the function. Okay. Now, I'll talk about number of Fatou components. So because maybe I'll need this thing, so that is why I'm mentioning it here, that for a rational map of degree at least 2, or even you don't need a degree here. So if R is a rational map, just a rational map, then it has either 0 or 1 or 2 or infinitely many Fatou components. So that means you cannot have any rational map for which it has three Fatou components or 4 Fatou components. So either it is 0 or 1 or 2 or it is infinitely many. So for the infinitely many case, we have seen that example of Cantor set. So maybe I can show it here again, that yes, for this function. So see the Fatou set. No, for this case, the Fatou set has exactly one component, which is the basin of attraction of infinity. And for this case also, it has 2 components, the interior and the exterior. And only one Fatou component is known to us, because in that case, the Fatou set you can take it to be just in the all C hat. And the 0 case is also known, because when the Julia set is completely C hat, then you will not have any Fatou component. Yeah, so these are you can check, these are very easy. Okay, now okay, so this is the number of Fatou components. Now I'll talk about that, like what type of Fatou components can occur in a like for a Russell map. So like so there are 3 kind of Fatou components, first of all. So first one is I'll say one is periodic. Periodic means what? So you have some Fatou component here, you map this component, and after some sort of iteration, it comes back to itself. So this is called periodic. Okay, so one is called pre-periodic. So pre-periodic means, suppose you start with some Fatou component, and you take the iteration, and suppose after some iteration, it comes back here. This is the first stage, this is the second, this is third, this is fourth, and after fourth stage, it comes to second. And once it comes second, it again goes 3, then 4, and then again comes to 2. So that means it cannot revisit the Fatou component what we started with, U. But in this case, I will say that U is a pre-periodic Fatou component. That means U is not periodic, but some, I'll write it, U is not periodic, but some iterated image of U is periodic. So this is called periodic Fatou component. Sorry, pre-periodic Fatou component. The third one is that wandering. And I will say something about the existence of this wandering domain. So wandering means what? So it is like this can be understood in a simple way, that if you start with some component, it goes somewhere else, then it goes somewhere else, and it never comes back. Even it never intersects with the previous P images. And it goes on, and it will never come back. So that means okay, I'll write R. R N U intersection R M U is always phi for all M N in N union 0. Okay, so this is wondering. So for the rational case, this periodic Fatou component and p-periodic Fatou components are the only Fatou components. So there does not exist any Fatou component for the rational map which are wandering. So this was proved by this is big result called no wandering domain theorem by Dennis Sullivan, for which he got the Abel Prize. Yes.
Sukant,
Yes.
whenever you have defined the definition of a wandering domain, I think M is not equals to N also, no? Here M is not equals to N.
Yes. Because
Yes.
Yeah. So the purpose of defining this wandering domain here is of great importance, because these kind of domains exist for the transcendental case only. So till 1985, it was not known whether wandering domains exist or not. But once it is proved, it was a groundbreaking result by Dennis Sullivan. Okay, now, yeah. So these are the only two possible Fatou components, like either periodic or periodic, and that's it. So now we will see. So that means it is enough to study the periodic Fatou components, because p-periodics are not that much important, because once it is p-periodic, so after taking some finite iteration, I'll get a periodic Fatou component, right? So it is important to study what are the periodic Fatou components of a rational map R. And I will say in a minute that there are there can exist one more different type of Fatou component for transcendental case. I'll say it in a minute. Okay. So there are 4 possible cases. That means if you have a periodic Fatou component, it will be one of these 4 cases. The first one is that it is either attracting So attracting, okay. So once I say about periodic Fatou components, so periodic means you can say like Rp of U. So this Fatou component you can name it by U. So Rpu is U. But be careful, this equality does not hold for transcendental. Rather, for transcendental case, we will write it as this is a subset of U, because for transcendental case we may have omitted values, but for rational we don't have any omitted values, so this will be exactly the same. Okay, so okay, now for attracting case, so if U is my periodic Fatou component, and obviously here P is the smallest, so it is always trivial that P is the smallest natural number. So if U is such that there exists a point, say Z0 in U, so that FNP, be careful here, it is FNP of Z0 goes to not Z0, Z goes to Z0 for all Z in U. And obviously when n goes to infinity, because we are taking iteration, so when all the points are going to this point Z0 under iteration of f in p, so we call this Fatou component to be an attracting Fatou component. So you can understand it like this. So here you have Z0, and you are starting with a point Z and iterating with under this map f in p, and it comes to this point Z0. The second one is that this is called parabolic domain. So this is quite similar, that in this case, what happens that there exists a point. So point means obviously I'm saying this point is p periodic. So I should mention here there exists a p periodic point. There exists a p periodic point p in the boundary of U, so that the same thing holds. So what is the picture in this case? So same idea. So here the only difference is that the point lies in a boundary, and you are starting with some point z here, and you are when you take the iteration under f and p, this z converges to z naught. So yes, so I'll give you some examples. Maybe yeah. So maybe it is correct position to give such examples. Okay, so maybe I will show you. Okay, this picture came earlier also. So okay, for the attracting case, I'm showing you that if you take your fz to be z minus zq minus 1 by 3z square. So this is my rational map. Then it has attracting domain, and the attracting domains are here. You can see by given in three colors. So the blue region, red region, white region. These are attracting domains. And even if you take a point here, it comes here, 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 and then comes here. And after certain iteration, it converges to this converges to this point. But be careful when I'm talking about just component. So this is the component, and you can consider this to be a pre-image of this component. Okay, now the second one for the parabolic case, you can so for the parabolic case, the example, what was the example? I could recall. Okay, these are not that much trivial. For the parabolic, this is for attracting. So for the parabolic case, this is h equal to j to the power 5 plus 0.8 0.4 I z 4 plus z. So in this case, the picture will look like so here maybe I'll leave this. So I think yeah, this is the way. So here you can see that you have a point. You have a point here where every point is converging. So this is the case for this is the parabolic case, and okay. So apart from these two things, these two cases, the third case which can arise is a single list. So what it is, okay, let me tell you quickly that a single disk, it is a periodic Fatou component such that the dynamics of RP, again I am writing RP and F. Okay, here I have written F, so I should write F. The dynamics of FP, because I'm talking about P periodic Fatou component, that is FP is conformally conjugate to an irrational rotation of the unities. This is the unities. Okay, so actually what is happening here is that so there exists an analytic homeomorphism say phi from this U to D, D is the unit disk, such that phi compose Fp compose by universe. This is of this form, means this function is an irrational rotation, while your alpha is irrational. So alpha is irrational, some irrational. So that means the idea is that, so suppose you have some domain periodic component under Fp, it is again U, and you are having map P, you are having map P, and this is the unit disk, and again this is your unit disk, and this map is P, F, P, P inverse. So here, so the map is acting like a rotation. That means if you consider any Jordan curve, in particular any concentric circle, if you consider any concentric circle here, the circle will remain itself. The only thing is it will be just rotated. So that means you can, if you can choose any, if you just choose any Jordan curve from this U, then under Fp it will be again the same Jordan curve, but it will be just rotated. So that means you can understand this Siegel disk as a collection of infinitely many Fp invariant Jordan curves. So let me write it here. U can be understood as the union of infinitely many Fp invariant Jordan curves. So right, so this is a setup. Okay, now the same setup can happen for this, which is called harmony. So I'm telling you what it is. So the same thing happens. The only difference is that this is not simply connected Fatou component. This is doubly connected. So harmony is always doubly connected, and your Siegel disk, this will be always simply connected. So the setup is quite similar. So you have some doubly connected Fatou component here. So it is a periodic Fatou component. This is invariant under Fp. Similarly, you have P here, you have C here, you have, instead of disk, you have an annulus here. So this map phi Fp P inverse is an irrational rotation on this annulus. This is for some R. So the same setup, same idea is happening here also, but the conformal conjugacy is happening on an annulus instead of these unit disk. Okay, now, so maybe I'll give you some examples. So the like possible like what can be the possible picture of this? Yes. So where should I put it? Maybe first let me show you. So see. So these are the simply connected Fatou components. These are Siegel disk, and inside this you can consider as a collection of or union of infinitely many invariant Jordan curves. So these are the Siegel disks, and infinitely many such Siegel disks are here. Okay. So let me keep it aside. Yes.
I have a quick question. Like,
yes.
are they Siegel disk or harmonic always bounded, or it can be unbounded?
No. No, this is not
So
the case.
we cannot say anything about boundedness.
No. I think so. Yes, because it is not necessarily bounded. Yes.
Okay. So we cannot say anything, huh?
Yes.
For
So
okay, fine.
Yeah. So because this, so remove these circles because let me keep it here. Now, so this was Siegel base. Now this is Harman ring. So the same kind of picture will appear. But the construction of Harman rings are not so easy. So as you can see here, the structure is like you see. So this is your like this is the thing like where you will have doubly connected Fatou components. So everywhere the same kind of structure you can see. Okay, okay. So maybe I can write the functions for this is the example of this is Harman ring. So yeah, this is z square into z minus 4 by 1 minus 4 z, where your t is some number which is 0.6151732 something. And for the Siegel disk, the example you can talk about is, so these are they are in the book. So if one is interested, one can visit into z plus z square. Okay. So maybe I'll just quickly say something about one more Fatou component and then I'll stop. So okay. So this is an important remark that Harman rings do not exist for polynomials. So maybe I can give you the hint. You can, if one is interested, one can go or go with the proof, because so if you just consider a Harman ring, say this is doubly connected Fatou component, then you can always consider a Jordan curve gamma such that the B gamma, that is the bounded complementary part, B gamma is the bounded complementary part, means this, such that B gamma intersects Julia set of this polynomial, because this is in the Julia set, because the boundary of this Fatou set is Julia in this case. So it will always intersect the Julia set. So the hint is that one can show that my map polynomial, so if you consider the iterates Pn is normal, not is not so normal, is uniformly bounded on B gamma, and that will just directly give you your answer that in this case you have D to be a domain of normality for Pn, which is not the case because this intersection is always normality. So yeah, one can go with this hint. And yeah, the last thing what I will say is this is a Baker domain. So yeah, so Baker domain does not exist for rational maps. So this is only for transcendental. So I'll just quickly say the definition and I'll stop. So yeah, so obviously this is not so trivial. You have to just analyze some functions, then you can understand how, like what kind of configuration of this Fatou component is. So this is a periodic Fatou component, say U, and say period P, then there exists a point z0 in the boundary of this component such that if in P of z goes to z0 for all z in U, but if P z0 is not defined. So here is the only difference. Because ultimately, if you just consider this is nothing but looking like the definition of a parabolic domain. So sometimes we call this Becker domain to be an essentially parabolic domain. So the only problem is this case, which does not occur for rational map. Okay, so I'll not go in deep. If I just talk about transcendental functions in other lectures, then I'll talk about all these things in detail. Okay, so yeah, I think I should stop. So yeah, so these are the only possible Fatou components for rational maps, and other than rational maps, wandering domains and Becker domains, these two domains can exist for transcendental map. Yeah, there are many examples. Okay, I think I should stop. If you have any question, you can ask.
Thank you, Sukanta. Do we have any question?
Yes.
If not, Sukanta, I have a question.
Yes.
Regarding the sigil disk.
Mm-hmm.
Can you please go back to the definition? Yeah. So it is simply connected, basically.
Yes, correct.
Yeah. So, is there any result regarding the boundary? Whether it will be whether the boundary of sigil disk will always be a Jordan curve?
No.
Do you have any example?
No, I cannot. I have to just go with the things, but I don't know right now that whether in what condition the boundary will be Jordan curve, or in particular you want something more for the boundary.
No, it's a simply
whether
connected.
they
So
are,
that's a natural thing to ask whether the boundary is Jordan curve or not. Yeah, that's why.
Okay. No,
Okay,
I
fair.
am not sure about that. Yeah, I just have to go through the things. Yes.
Okay. We'll talk about it.
Yeah.
Okay. So, any other question? Okay. So if not, thank you, Sukanta, for such a good lecture series.
Okay. Thank you.
Okay, so we'll close the session.
Okay.
Agniva,
Yes.
can you stop the recording?